Welcome. This question says, what is the current flow through the 5 ohm resistor? And if we look at this circuit, we see that the 5 ohm resistor is here. And although at first it looks like a relatively simple circuit in that there's only 3 resistors, we then see that there's 2 power supplies. And multiple power supplies is like the dividing line between simple circuits and more complicated circuits. And so we're going to solve this using Kirchhoff's laws. And it's a more formulaic approach to solving more complex equations. And there's 2 basic rules we have. We have a junction rule and a so-called loop rule. And a junction rule is all about places like this where the wires come to a single point. That's a junction. And basically what we have to do is we have to decide what direction we think currents flow into and out of the junction, and we have to give the different currents names. So I'm going to call this I1 and this I2 and this I3. Now I drew I1 going towards the junction, I drew I2 going towards the junction, and I'm doing I3 coming away from the junction, and they are arbitrary choices. The important thing is that having made those choices, I will take them into account as I do the mathematical bookkeeping, which I begin to do now. So this is a formulaic approach to problem solving. So the first rule is the junction rule. What it says is the sum of the currents at a junction equals 0. What that means is that the current in must equal the current out. So if I look at this, the way I have drawn my diagram, I can say I1 plus I2, they're the currents in, must equal I3. So there we are. That's the first bit, one equation. My second bit I'm going to get from this loop of components. And there's a loop rule, and it says the sum of the voltages in a loop equals 0. What that means is the EMF produced by a power supply plus the potential differences across the, in this case, resistors, must sum to 0. Basically, the voltage I create in the power supply is used up or dropped across the components in the other parts of the loop. And for this, I need the aid of a abstraction, and so I am imagining a loop of interest. I imagine taking my point of interest around this loop. It's not the current, it is a point of interest, a perspective if you like. And I've chosen to draw this in a clockwise direction. Why? It's my habit. It's as simple as that. And there are 2 rules that I need to know now. One is, I'm both concerned the signs I will give to the EMF and to the potential differences. It's a way of getting the signs to work out. And so the first rule is, if the loop that I chose to draw, as it passes through the component, I don't draw it on the actual wire because it gets too difficult to see. I draw it inside the wire, but I'm imagining my point of interest going in the direction of the green arrow, so it comes up and it leaves the power supply via the positive electrode. If the loop leaves a power supply via the positive electrode, that's a positive EMF. And if the loop were to leave the power supply via the negative electrode, that would be a negative EMF. And again, how do we decide what direction to draw the loop in? It's completely arbitrary. As long as having drawn it, we write the correct equation associated with that drawing, everything will be fine. So I look at this and I say I left via the positive electrode, so that's a +6 volts EMF. Well, there's other parts to this loop, and these are potential differences, and the voltage drop across them is IR. Well, I can see this is going to be I1 because that's the current flowing through this 3 ohm resistor. So this would be I1 times 3. Well, let's put it down as 3I1. Now, the question is, what sign is it? If the loop passes through a component, in this case, left to right, and that is the same direction that the current passes through the component, and the way I drew the current, it was from left to right. If both the loop and the current pass through the component in the same direction, it's a negative potential difference. It's just bookkeeping. It's a way of making sure the signs work out, and opposing things have opposite signs. If I look at this third component, then again it's a potential difference, so it's the current times the volt times the resistance, which is I3 times 7. Let's put that down as 7I3. And again, what sign is it? Well, my current is flowing downwards and my loop is flowing downwards. It's the same direction, so that's a negative 7I3, and that sums to 0. Okay. I have 3 unknowns in my equation. In my problem, I1, I2, and I3, so I need 3 equations. So let's do a third loop. And I like to just keep things as simple as possible. So again, I'm going to do a clockwise loop. I'm going to say the sum of the voltages along the gray loop is equal to 0. And again, I'm going to, well, which terminal does the loop leave the 9-volt power supply via? Well, it leaves it coming out of the negative terminals. That would be minus 9 volts. And then, doesn't matter which one of these I take first. Let's take the 7. This is going to be IR again. Well, let's say RI. The potential difference is R times I, which is 7I3. And here, the current is flowing down, but the loop is going up. It's in opposite directions, so that would be a positive potential difference. And let's look at this 5 ohm resistor. Again, it's a potential difference, and the potential difference is IR. In this part of the circuit, the current is I2, and the resistance is 5, so let's put down 5I2. And again, let's look at the directions. The current is flowing to the left, but the loop is going to the right. Opposite directions means a positive, equals 0. So I have 3 equations and 3 unknowns, so it's solvable. But let's solve it. And I suppose the first thing I need to do is, so what I tend to do, again this is force of habit, what I tend to do is I recognize that every equation contains I3. So let's substitute into the first equation to get I3. So in this green equation, this second equation, I'm going to say, oh, I1 is equal to 6 minus 7I3. I took that 3I1 to the other side. And so I'm going to divide by 3. So let's double check on that. I took the 3I1 to the other side, became positive. I had 6 minus 7I3 left behind, and then I divided by that 3. And then if I look at the next equation, I'm going to try and find I2. So I2 is equal to, and well, let's move the 9 to the other side, so that's 9, and then let's move the 7 to the other side, so that's minus 7i3 over 5. Just double check that. So my 9 went to the other side, became a positive. My I3 went to the other side, became a negative, and then I have divided by 5. Yeah. So then the rest is math. So I can say, look at this first equation, I1 plus I2 equals I3. Well, here's I1. So 6 over 3 minus 7 over 3 I3, that's I1, added 2. And next we're going to add on I2. Well, this is I2, 9 over 5 minus 7 over 5 I3, that's I2, and that's equal to I3. So then let's collect terms. Well, 6 over 3 is 2, plus 9 over 5 is 1.8, is equal to 7 over 3 is 2.3, and it becomes positive, plus 2.33, but we'll say 2.3. Added to this, 7 over 5 goes to the other side and becomes positive, which is 1.67. Oh, no. Sorry, I'm doing things in my head and it's always a bit dangerous. So this is 7 over 5 is 5 over 5 and 2 over 5, 1.4 plus, that's 1.0 I3. So I took that 7 over 3 to the other side and got 2.3, it became positive. I took that 7 over 5 to the other side and got 1.4 and it became a positive, and there was that 1 left behind. So we get 3.8 is equal to 2.3, 3.3, 3.7, 4.7. 4.7 I3. So I3 is equal to 3.8 over 4.7, which equals 3.8 divided by 4.7 equals 0.81, which is 0.81 amps. So there we have I3, but the question asks for the 5 ohm resistor, which is I2. And so what do we do about that? Well, we just substitute. So we say, okay, so this tells us that I2 is equal to 9 over 5 minus 7 over 5 times 0.81. So this is 7 divided by 5, enter, times 0.81, enter. So this is going to be 9 divided by 5, enter, minus 1, sorry, I'm making hard work of this, minus 1.134. And this equals I2 is equal to 0.66 amps. There's my answer. The fact that it's positive means that by chance I pick the right direction, the correct direction. If I'd picked the other direction for I2, then signs would have changed all over this calculation. I'd have got the same numerical value, but the signs would have changed. So that's Kirchhoff's laws, or some people call it Kirchhoff's laws. It's very formulaic. It's 3 steps and then a bit of math. It's incredibly useful. Remember, everything in physics is introduced because it makes life easier. And if you try to solve this using V equals IR and other conceptual approaches, it would be very hard. This is a formulaic way of dealing with more complex circuits. It works very nicely. And so there we have it.